Right, so the time has come to discuss line integrals in space. We discussed them in a plane, and we really discussed them in a one-dimensional case with the idea of a single variable integral, which is a very easy idea. So we went from discussing pretty much the single variable integral, which is consider a rod. I give it a density function, call that rho, and I find the integral between over the length of rho dx, right? And then what we did is we took a two-dimensional case in last video. We called that c, and we assigned that pretty much a density function as well. Then we need to parameterize it. Now what we're going to do is we're going to consider a three-dimensional case where I have a space and then I've got some curve up in here, and that has its own density function, rho. Now we got to figure out how to deal with that. It's quite easy. We just need to remember a little bit from the first unit when we discussed parameterizations of vector equations for lines. And obviously there are some parameterizations that I think you should know for like a helix or a circle, obviously, or a cylinder or a sphere or something like that. But we should be good. We should be all set to go. So the definition, let x, y, and z be a set of parametric equations. So the point x, y, and z is defined by x equals x of t, y equals y of t, and z equals z of t. So we can write this in vector form such that our position vector r is defined by x of t, y, and t, and z of t as its components. So you could write that in either your vector equation, or you could write it as a parametric set of equations governing your position, right? Anyways, what we can do now is we can expand this idea. So it's really very straightforward. This should be an s and not an x. Anyways, if I want to integrate along a curve the function with respect to some displacement, I'm going to go from t equals a to t equals b of f of x of t, y, and t, and z of t. And then I take the square root and sum all of the squares of the partial derivatives. Then I integrate with respect to t. So it's the same thing as the last one, we're just bumping it up another dimension. Again, the intricacy here is going to come in the form of finding the parameterizations that you need, right? So what we do from here is we take the integral and put it into vector form. So what you'll note here is if I remember that this is my vector, well then this is a function of x of t, y, and t, and z of t. Well, what is also a function of x of t and y, or what is x of t, y of t, of z of t? Well, that's my position vector. So I get f of my position vector, and that's with respect to t. Well, then also you have this square root thing here. And, well, what does that look like? Well, the square root is, or the square root of the sums of components of a vector is its magnitude. And obviously we're taking all of the derivatives and then squaring them. So we get is the derivative of the position vector with respect to t. Then we integrate with respect to dt. So what we can really say is that if I just want to find the length, in the case where my function is 1, so this is just finding the arc length, I can just take the integral between a and b of the magnitude of r prime of t dt, okay? And this should be very straightforward because in the case where we have our original equation for the arc length, that's what that will reduce to. So that's very nice that we have that. And sorry, I dropped the t equals here. It's implied that we're integrating with respect to our t bounds. Then also note that if I want to find the vector equation for a line, and I'm given two vectors, my initial vector and my ending vector, then I can define the vector function as being r of t equals 1 minus t times r naught, first vector, plus t times r1, the second vector. And then t will go between 0 and 1 for this. So that's how we set up this vector equation such that t can go between 0 and 1. So if you're integrating between this line, if you're integrating along a line between any two vectors, you'll always integrate, so your integral over the curve will go to the integral from 0 to 1 dt, and then whatever you have inside of there. All right, let's do a couple examples. So this one's from Stewart's book. Let's try integrating the contour integral of y sine z ds And C is going to be some helix, so we get a helical structure for this guy. Always fun. So we start with a unit circle, then we kind of go up, and then up, and then it wants us to go from 0 to 2 pi, so we're only going to go up to 2 pi for our rotation. Now we want to use the parameterization that they give us, which is nice of them. That's a t there. X is equal to cosine of t, y is equal to sine of t, and z is equal to t. That should be fairly self-explanatory, and it should make sense. We're taking a unit circle and we're stretching it and decomposing it. So what we can do now is we can plug this in. We can plug everything in. We know our bounds. We know how to find the differential element. And we know all of our parameterizations. So we get the integral between 0 and 2 pi, sine of t, and then z is t, so we get another sine of t. We take the square root of sine squared t plus cosine squared t, taking all those derivatives and squaring them, plus 1 dt. So what is nice about this? Well, sine squared plus cosine squared reduces to 1. Unfortunately, we still have that 1 there, so we're not going to get like a perfect number, but we get the square root of 2, but that's fine. We can take that out. We get the square root of 2 times the integral between 0 and 2 pi of sine squared t dt. Now, sine squared integral is one that you need to use the double angle formula for, I believe it is, or well, it's the cosine double angle formula. Anyways, you can find that integral fairly easily. I'll forego that. What you get is you get a half root 2 t minus 1/2 sine 2t between 0 and 2 pi. Then you get pi over 2, right? Okay, so that should make sense. So that's an integral in 3D space. It's fairly self-explanatory. Let's try just another one, and we'll test out all of this vector stuff. So we'll find the integral, and this is a new way of doing it. We can separate these sometimes if we want, the functions and the differentials. If we want to separate them, we are allowed to do so. So we're finding the integral of y dx plus z dy plus x dz. And we're going to be doing two curves. So the first is a line from point 2, 0, 0 to 3, 4, 5. Let's see if we can draw this out. Knowing myself, probably not, but that's all right. 2, 0, 0, so that's going to be there. And then 3, 4, 5, we're going a little bit over here. We're going a little bit up. Then we're going a little bit over this way. So that will be our first point. And we're just taking a straight line up there. Okay. Then our second curve is going to go from 3, 4, 5 to 3, 4, 0. So we're going all the way back down. All the way back down. That should end about there. So there are our curves that we want to integrate over. There's C1 and there's C2. And now we can come up with vector equations for these. We're going to use the vector for this. So we go over C of f of r of t magnitude r prime of t dt. Let's try this. So the first one, well, we're starting with the vector 2, 0, 0, or we can call that a vector 2, 0, 0. It's an ordered pair, an ordered set. We multiply that by 1 minus t. Then we add t times 3, 4, 5. T will be between 0 and 1. So now what we can do is we can set up a series of parametric equations. And this will give 1 for x, 1 for y, and 1 for z. What we can do is we can then plug that into this equation. We gather the quantities, dx, dy, dz, and the quantities x, y, and z. And then also we're going to do the same thing for the second one. Obviously, it's the same sort of deal. We can just add all of them together, because if you remember, if I wanted to take the integral over one curve, I could make that the integral of over the first plus the integral over the second, plus however many other integrals I want to do. I mean, theoretically, I could have gone halfway and then did 3, but you can do one integral over the line, may as well. Anyways, you get the integral of f ds. We do the first one here, and we take all of these, and we find all of the x values, y values, and z values, and all of their derivatives. When we take the derivative of the x value, the dt goes off implicitly. We get 2 plus t dt plus 5t plus 4 dt plus 2 plus t times 5 dt. I really don't like the notation that they use here, putting multiple differentials for a single integral. I don't like that. Whatever. and then we add the curve 2. Now, if you'll notice with the curve 2, from the parametric equations that we get, a lot of the derivative terms, these dt's, are going to be 0. So that kills off a lot of these values here. So we only get 1. We get the integral between 0 and 1 of 3 times negative 5 dt. When we add all of this together, we get 19 over 2, right? Okay, so we've covered all that we need to for line integrals, really. It's not too complicated as long as you know the parameterizations. That's the complicated part. The rest is really Calc 1, Calc 2, just plugging things into the integral and doing an easy integral, right? We're past doing by parts integrals and whatnot over here. We're just applying new concepts. Anyways, now in the next video we want to apply this to vector fields, which we learned a couple videos ago. Talk about the idea of a conservative vector field, which we covered a while ago, and what it means for line integral. So it turns out if you have a conservative vector field, then if you take the integral over a closed loop on a conserved vector field, then you get 0. So what that means is that it is path independent. No matter what path you take between 2 points, the integral value will be the same. Okay, or the work done that you've done, theoretically the work. We'll talk about work later. Work is something that we covered in single variable calculus, and we need to expand it because now we have the notion of a potential function, we have the notion of force as a vector field, not as a function. So we need to apply a line integral to it, and then work is going to make a lot more sense, or maybe it'll make less sense, maybe we'll make it more complicated. It'll be more complicated, but that's fine. All right, we'll see you in the next video. Thanks for watching.